Okay, hi everybody. My name is Servén Marín. I am a senior software engineer at Red Hat, and we're going to be talking about automating GPU infrastructure for Kubernetes for container Linux. This sounds like really specific to container Linux, but I think that you'll find that it actually generalizes well to Linux in general. And we're going to be doing a little bit deeper dive into some of like the nitty-gritty of getting kernel modules and stuff set up for your nodes. And I think that this will complement well some of the other talks we had in Kubecon so far related to GPUs, like Anod's talk yesterday and Rohit's talk just half an hour ago. The goal really is to take you from thinking that you know everything about compiling GPUs, GPU drivers, to doubting everything you know, and then to, once again, believing that you kind of know things as well. And if the demo gods like it, we'll have a demo as well, where we'll bring up a Kubernetes cluster, accelerate with GPUs, and all of that should take under 10 minutes. So let's see what happens. First and foremost, the astute observer will see that all of the slides are branded with Red Hat, but the shed said that I work at CoreOS. This is not a mistake. CoreOS was recently acquired, and we very happily join everyone at Red Hat. If you have any questions for CoreOS related things or Red Hat related things, please grab me or any other Red Hat person, and I'd be very happy to talk to you. So a little bit about me. Like I said, my name is Lucas. I live in Berlin. I am an electrical engineer. I studied robotics and controls, and I work for the last year and a half on the Tectonic installer at CoreOS. And now I'm working on bringing everything that we learned from Tectonic onto OpenShift. In my spare time, though, outside of Red Hat and outside of Kubernetes, I like to work on machine learning projects and controls-related things. I work a lot with this other guy. His name is Daniel. He's my twin brother. He also has a funny-looking GitHub avatar, and we're always working on machine learning projects together. So one of the issues that we see when we're working on projects for the first time is that since we live so far apart, sometimes collaborating can be difficult. For example, we're sharing our code, maybe on a Jupyter notebook or something, but we also want to share our hardware so that we can both train our models in an accelerated way. It makes no sense if I have the hardware and Danny has to wait for me to be up so he can send me code and I can train something. That just doesn't work. But luckily for us, we are at Kubecon EU, and if we just put our workload onto Kubernetes, it solves everything and we can go home early, right? What we will see is that maybe it's a little bit trickier than this. Right here, we have the IKEA instructions for how to build a Kubernetes cluster powered by GPUs. I wish it was this simple. You just plug these things in together, but maybe it's actually not. So say that you have your CUDA-powered workload, be it TensorFlow or Jupyter Notebook or something, and you package it up in a container with all of its dependencies. You use Kubernetes to manage this container, its lifecycle, expose the service to the internet so that I can log in on a website and be like, Jupyter Notebook, run these commands. I accelerate everything using Nvidia, and then personally, I run all of my Kubernetes clusters on top of CoreOS just because I like container Linux, because it gives me like low maintenance overhead, everything updates automatically, and this is all great. But as we're going to see, some of these components are not very obvious. We know how to plug in a workload into Kubernetes. We're all at KubeCon. We've done this before. Just last talk, half an hour ago, Rohit explained in very great detail how you can plug Kubernetes into NVIDIA GPUs and how to use a device plugin to accomplish this. But the one thing that's still a little bit questionable for a lot of people out there and is a little bit fragmented in the community is how do you get your GPU drivers and how do you get NVIDIA GPUs working on Linux in the first place? So really quickly, we have a pop quiz. I guess you guys were not expecting this. It should be very easy. If you guys were just in the last talk, Rohit actually covered each of the 4 points that I'm looking for. Does anybody know what are the 4 things that I need to get my GPU working on Linux machine? Can you just call them out? I need drivers. This is actually 2 of the things. So this gives me the kernel modules and the libraries. What else do I need? I need GPUs. This is the obvious one that a lot of people miss. And what's the last thing I need? Well, I need my CUDA libraries on my workload, right? If I want to use a CUDA accelerated workload, I need to have CUDA libraries as well. OK, so here we have an example of what our anatomy of a CUDA workload might look like. So I have my application at the very top. This container comes packaged in with my CUDA libraries as well, my user space, my user level libraries. I need my NVIDIA device files that get created. And these are created once I've loaded my kernel modules. I create the device nodes. And obviously, at the very bottom, I need my GPUs as well. So using the knowledge that we just had in the quiz, we can fill in our IKEA diagram a little bit more. And we can see that the GPU drivers, the CUDA libraries come for free. Thankfully, all the folks at NVIDIA are providing Docker base images for CUDA that package the CUDA libraries for us, so we can build our containers on top of that. That's very great. That comes for free. Assuming somebody in the audience buys me a GPU, we have a GPU, so we can check that off. The two things that we don't really know that are kind of still question marks are where do the NVIDIA libraries come from? And then also, where do the kernel modules come from? And this is actually kind of a trickier question. It turns out that the Linux community is a little bit fragmented here, right? Like, for example, if I am on Ubuntu, I can sudo apt-get install my NVIDIA drivers or something. If I'm on Fedora, I can do the same thing. But what happens if I'm on container Linux where I don't have a package manager, right? And then, even if I did have a package manager, what happens when my OS upgrades and my kernel version changes and now my kernel modules don't work? What happens then, right? Do I just have downtime on my server? Do I have to go in and manually fix this again? What do I do? So even though we don't have a package manager, let's not be deterred. Let's get our kernel modules built for container Linux. So the first thing we all do when we want to do this is we go to the docs, right? And we go to the docs, we go to the documentation website, and we say, all right, which packages already exist? CentOS, Fedora. I don't see container Linux on here. So I'm sorry, I wasted everybody's time. There will be no GPUs on container Linux. You can all go home. This is it. But somebody says, Lucas, don't give up. After all, why don't you just download the NVIDIA installer and compile the kernel modules yourself? You guys are very smart. I'm not surprised. We are at Kubecon EU, one of the greatest gatherings of minds in all of southern Copenhagen. So yeah, let's do exactly that. I'll take your advice. Let's download the kernel, the NVIDIA installer sources, and compile it ourselves, right? What could go wrong? Let's see. All right. So I download, I curl it down. All I need now is to run GCC on my container Linux machine, except it turns out that GCC is not installed on this minimal OS. Who would have thunk it? Okay. What do I do now? This is obviously not going to work, right? This is just a no-go from the beginning. Okay. Your guys' next intuition, obviously, is this is a container OS. Why don't we just run the build in a container? If I Google Docker GCC on Google, I get like 50 hits, right? Okay, so great. I'll Docker run GCC, download the NVIDIA installer, and then I follow the doc some more, and it says, okay, now you just have to provide the path to the kernel sources. All right, but where are the kernel sources on container Linux, right? Like, this is a minimal OS. Again, this doesn't come packaged in the OS. Where does this come from? We shouldn't have been surprised. Of course, we were going to need the kernel sources. At the end of the day, we're compiling kernel modules. It makes sense that we have to link against the kernel sources, no? The problem is actually even a little bit trickier than this. If you notice, we're running a completely arbitrary version of GCC, right? Ideally, we should be running the same tool chain that was used to compile the kernel to build the kernel modules as well. And this could this could produce completely unexpected results. We don't know if this is going to work or not, even if we had the kernel sources. So, this is also just no-go. You guys had very good intuition, but we got nowhere. Your advice, it was very, very well-intentioned, but we're no closer to getting GPUs on container Linux so far. The avatars, my GitHub avatar is getting very impatient, and I still don't have my GPUs ready. So now what do I do? Okay, well, I Google CoreOS container Linux kernel modules. The first result is some docs explaining how to do this on container Linux. Why didn't we do this in the beginning? It turns out that there's docs that document exactly how to compile these kernel modules. So really, getting kernel modules working on container Linux should be as easy as just running these steps. In fact, if the steps are very well documented, automating the compilation of these kernel modules should be as easy as just scripting these steps, right? So now I can automatically compile my kernel modules and my NVIDIA libraries for container Linux just with one script. If I look out in the wild, there's actually a few projects that already do this. I went to KubeCon North America 2016, and one of the speakers, Rudy Curiato, I think I said his name right, from Clarify, he gave a speech titled State of the GP Union, and the very last slide made a very brief mention to this one project called, aptly named CoreOS Nvidia, and it does exactly that. It just automated the instructions that we saw in the CoreOS documentation, and if I say CoreOS Nvidia build, my version of Nvidia, it'll produce the kernel modules and also the libraries. So great. Is that great? Does that solve all of our problems? It turns out not really. Okay, so now I have a way to automatically produce my kernel modules, but how do I automate this script, right? Next week, when Container Linux releases a new version, and I'm on vacation, who's going to log into my machine and rerun this script and say, hey, build a new version for the new kernel? Or, what happens if I want to change to a new NVIDIA version? Then what happens? How do I automate this? Secondly, how can I make this work in a way that's native to Kubernetes, right? Ideally, I don't want to have to SSH into my machines, or I don't want to have to create a cron job to do this or anything like that, right? I would want to just have a pod, something native in Kubernetes that does this automatically for me. So the obvious answer is, Lucas, why don't you just shove it all in a container? And this is the right intuition. Putting this build script into a container is definitely the right idea. The nuances are a little bit trickier because Container Linux, the instructions provided for building kernel modules, they tell you to download a developer container that contains, these include the kernel sources as well as the toolchain used to build the OS. So the nuances of running this container inside of another container is a little bit tricky, but this is definitely the right intuition. In fact, if I run this inside of a container, I can run my kernel module compiler in a daemon set that's scheduled onto all of my GPU nodes. If I schedule it onto every single GPU node, I no longer have to manually SSH onto my machines and do anything, right? Every single time that my machine updates and reboots, my kernel modules will get automatically recompiled for me. So this saves me a lot of headache. In fact, this is exactly what is done in the wild by the Google Cloud Platform folks. So Rohit was just speaking about this. They created a container that is exactly that for cost, the container optimized OS. Like Container Linux, it is very minimal, but this container is a script that downloads the cost kernel sources, compiles the kernel modules, and just dumps them in a host volume that later pods that need to use CUDA or whatever else can just consume those volumes. We can skip this and come back if we have time. So at the end of the day, if I have a daemon set that runs this container, compiling kernel modules for Kubernetes for any of my nodes is really as simple as just saying kubectl apply this daemon set. And that is the most Kubernetes native way I could think of doing this. Really quickly, I'm going to Terraform apply something so that by the end of this thing, we have a cluster we can play with. Okay, very cool. Okay, so this is it. Next what? Let's see. Okay, great. So now we know how to compile our kernel modules automatically, right? This is great. This gets a long way of the way there. But how do I consume these kernel modules and the libraries once they're on my machine? It turns out that getting these kernel modules and getting the libraries working with any sample workload is actually very straightforward. Here I have a toy workload that is an NVIDIA CUDA container, and I'm just going to run the NVIDIA SMI utility, which is the system management interface. It just prints out statistics about memory consumption, temperature, whatever, about the attached GPUs on your machine. And the only thing I really need to do is tell my container runtime to mount in my device nodes and bind mount my libraries. And then that's all I really need. One of the issues that we see with this, though, is that I'm leaning very heavily on my container runtime to do this for me. In fact, I'm leaning so heavily on it that I need to tell it exactly where my libraries are on my host and which devices I want to use. And if we try to extrapolate this to Kubernetes and we ask, how can we automate this exact same task for Kubernetes, it means that we would have to, in our pod spec, specify, I want to use a volume mount with these exact host path for my shared libraries. I need to, and then my application needs to know which device nodes to use. And this obviously is not going to scale well, right? It means that I have to very tightly couple the representation of my host to my pod spec. And now suddenly, if I want to share my pod spec across nodes that have my libraries installed differently or across different clusters, it's not going to work anymore. I'm going to have to modify my pod specs. Oh, very good. Let's see. So this is just doing some GPG stuff for our cluster. Very good. You guys should have told me. OK. It turns out that thanks to all the efforts that came into the device plugin system, in Kubernetes 1.10, oh, man, again. Let's see. OK. Thanks to all the work that went into the device plugin system, all of the work of having to buy mount in the libraries and stuff comes for free now. The device plugins developed by both Google and also by Nvidia take care of mounting in the libraries for us. And it means that we no longer have to specify in our pod spec explicitly, hey, I want to use these Nvidia libraries located here on the host, and my application doesn't have to know which device nodes to use either. In fact, the device plugin for Google, for example, is extremely simple. It's only a couple hundred lines of Go, and the code that does the mounting of the libraries is also similarly very simple. So like, it's only a couple lines, but it means this is the difference between having very tightly coupled pod specs to our infrastructure and having very loosely coupled things where we can just say in a pod spec, hey, require 1 GPU, and that's it. OK, so where are we now? After all of this, we know that we can use a GPU installer to generate our NVIDIA libraries, get our kernel modules, install the kernel modules, create device nodes. So that would be what? Everything here, right? This is everything that's done by the GPU installer. This is great. So it'll create device nodes that have to do with the GPUs that are attached to the host. And then the device plugin takes care of these other arrows. It's actually what's specifying which volumes I want to mount in to my containers so that my applications at the very top, be it TensorFlow or Jupyter or whatever else, don't have to know anything about the representation on the host. That's awesome, right? OK, so now what? If we go back to our IKEA instructions one last time, we see that we now have checkboxes on everything. We know where our CUDA libraries are. We have a GPU that you guys got me. We have our NVIDIA libraries compiled automatically, and our kernel modules as well. So this is going very well. What else do we need? I guess this is essentially all of the theory around automating the GPU infrastructure. Now we kind of want to take a look at a real-life situation. So without further ado, let's do a demo, I guess. What's going to happen in this demo? OK, so in this demo, if you want, you can follow along. It's on github.com/squat. This is my username, Kubecon EU 2018. We're going to be building a cluster using Typhoon. So this is a very minimal self-hosted Kubernetes cluster. We're going to be using GKE. It can honestly work on anything. I have a GPU installer daemon set that I wrote for container Linux. We can use this. Just last week, I found another one. So there's actually several implementations of these things. Like, this is one of the things where the community is getting very fragmented. But we have a GPU installer that we're going to use to compile the kernel modules. We have the device plugin that is in upstream Kubernetes. So as of 1 month ago, there is a device plugin in the Kubernetes repository in the cluster add-ons. And then we're going to run a neural network as our sample workload. And it's going to do some object detection for us. So let's see. Dun, dun, dun. Very cool, very cool. OK, so what do we have here? If you guys see, the Terraform here didn't finish running, so I'm going to use my other cluster that I just made this morning that is already built, and then apply all the Kubernetes manifest and everything that we need to it. Okay? So let's see if the demo gods are kind to us. Okay, very cool. So we already created our cluster. Now all the thing we want to do is let's get the nodes. Let's see how we're doing here. Okay, great. So I have a 2-node cluster. I have 1 controller and then 1 worker. This worker is, has a GPU attached to it. So let's take a look at what manifest we have here. We have our darknet, object detection deployment. We have our device plugin daemon set, and then we have our GPU driver installer daemon set as well. So let's kubectl apply. Let's see what happens, yeah? Very cool. That was extremely fast. Dun, dun, dun. OK, now what do we want to do? So we did the manifest. Let's look at the driver installer. Let's see how this thing is progressing. So again, this driver installer is running as a daemon set on all the GPU nodes, in this case, just 1. It's going to compile the kernel modules, put them on the host disk. It's going to mod probe, so it's going to insert the kernel modules. It's going to create device nodes that later we can use using the device plugin. OK, so let's take a look, yeah? OK, so it actually finished compiling already. These errors at the bottom are noise, but this should have worked just fine. So let's see. We can check the logs of the device plugin to see if indeed the device plugin saw that this is all registered. OK, this is apparently a device plugin on a different node. Let's see on the other node what happened. OK, very cool. So the device plugin here is registering a device NVIDIA 0. It's in healthy state, healthy state. So this is exactly what we were hoping for. Let's take a look at that node. If we describe the node, we should see that it actually has GPUs on it. OK, let's see. We have 1 NVIDIA GPU. And the capacity is here, yeah, perfect. So we have the GPUs, ideal. What else do we see? OK, let's take a really quick look at what the manifest for the workload looks like. So we have some standard deployment boilerplate. We have the command that's just running the neural network. And the interesting stuff is here. We're specifying 1 GPU, and we're also tolerating the GPU taint. Very cool. OK, quit. So the last thing we want to see is let's take a look to see if this container is already ready. Sometimes these things take a long time to download because the CUDA base images are pretty big sometimes, and depending on the network connection. OK, this already created the container. Perfect. And let's see the last thing. So let's check the logs of this. OK, great. So this neural network is running. And we're going to run. This is just a sample client app that what this is going to be doing is it's going to run some OpenCV. It's just going to be taking photos of me and submitting it to the cluster for some object detection. So this is me. It's just labeling me and seeing that I'm here. And this is all accelerated by CUDA. If I didn't have my kernel modules here and I didn't have a GPU, this would be taking like 10 seconds per image. But this is actually taking very little time. And most of the lag is actually just latency in uploading the images to the server. So this is all working. And what's the result here? So this is our demo. This concludes the interactive portion. How did I make this full screen again? Well, OK. So what happened here? We saw that very quickly, if we bring up a Kubernetes cluster, we can apply 2 manifests, have our GPU drivers installed, and we can get running with a workload super, super fast. What is missing here? One of the things that we alluded to earlier that are missing is that the GPU ecosystem is still very fragmented. So there's a different GPU installer for every operating system, or really that's like the way things are going in the wild right now. And in fact, there may be multiple implementations for every operating system, and this is also not ideal. Instead of us pooling our efforts, it would be great if we had some generic utilities that we could use for more of our infrastructure. What other problems do we have? There's also the issue that whenever I update my operating system, I still don't have zero downtime deployment. So if I do an operating system update, my GPU installer pod will get rescheduled onto my node. It has to recompile the kernel modules while this is compiling, so maybe 5 or 10 minutes. My workloads will be unschedulable. They'll just be pending. So I still have downtime. And then the last issue is that what about sharing my kernel modules? If I have 10 nodes that have GPUs, every single one is going to compile my kernel modules. It would be great if I could just compile them once and distribute them everywhere. These are all things that we still have to do. And these are some open questions. But with that, I leave you guys. Thank you very much. If you have any questions, please ask me. And otherwise, we can just chat afterwards, yeah?